Hi, welcome to Make Me a Research Consult. Today, we'll be looking at how to use the matrix algebra to resolve systems of equations. This tutorial is dedicated to a two-system equation. In most cases, you would have to do with resolving several equations. So today's discussion will focus on the types of systems equation you could have, a brief introduction to a matrix algebra, the approaches that are used in algebra, matrix algebra, to resolve systems of equations, and then we take an example using one of the approaches. Now, let's dive into systems of equations. We all know from studies that you could either have two systems of equation, which is shown up here, or you could also have a three system of equation. Now, the systems of equations depends on the number of variables that are in that equation. For instance, looking at this equation, 2x plus 12y equals 40, there are two variables, x and y. Now, to resolve this equation and find the values of x and y, you would have to resolve it using two systems of equations. In this case, one equation, then the second equation. Now, this economically will be used to resolve an objective function you were doing linear programming. Now, when we have three systems of equations, it means that there are three variables, x, y, and z. So that this equation, one equation, the second equation, and the third equation. So practically, the number of variables we have influences the number of systems of equations that will be resolved. So a two system of equation has two variables. A third system of equation would have three variables, and a fourth system of equation would have had four variables, right? So these are the types of systems of equations that we could have. Now, in our systems of equations solutions, there are two approaches that could be used. It's either the substitution approach or the elimination method. You would have videos on the substitution method, how to use to resolve two systems and three systems of equations. You could also have consult our videos to have a brief review on how to use the elimination method to resolve systems of equations. Sometimes they could be complex. That's how the matrices come in handy. With matrices, you could be able to determine whether there will be a solution to any systems of equation before you start working. So we have an introduction to that in other videos, but for this way, we are going to see how to use the matrices to solve systems of equations. Let's look at a matrix algebra in its brief way. Now, there are three matrix methods that could be used to resolve systems of equations, either two equations or three equations. You could use the inverse rule method, you could use the Gaussian method, and the commonly used Cramer's rule method. For the sake of this study, we'll be introducing ourselves to the Cramer's rule. In other videos, you could consult videos, also tutorials. There will be videos for the Gaussian method and that of the inverse method also. Now, to start with, whenever you have systems of equations, this is the meaning. First, let's take these two systems of equations. To write this or to convert this into a matrix, we would have matrix written as AX equals B. Now, by looking at this, you could see A would be called the coefficient matrix, which is basically putting all the variables together, aligning them. Then each coefficient is written in place as it appears here. So the A coefficient, the A, which is the coefficient matrix, A matrix, which is the coefficient matrix, is made up by substituting the coefficients 2, 12 for the first row, 2, 12, then 8, 4 for the second row. That becomes our coefficient matrix A. Now, the matrix X is called the variable matrix. And that is X variable in the first row, Y variable in the second row. If they were 3 variables, then the Z variable will be Z in the third row right here. That will be the X variable. Now, equals to B, the B is called the constant matrix. So B constant matrix is equal to 40, 28. So you can see we've been able to rewrite these systems of linear equations into a matrix as this. So A, matrix A times matrix X equals to the constant matrix. Now we're going to use this to solve the systems of equations. So let's get back to matrix approaches, like we said. Now, using the Cramer's rule, remember, we said there are 3 approaches. You could use the Gaussian method, you could use the inverse rule, and the Cramer's rule. Now, looking at the Cramer's rule, there is this rule that you need to accept. Now, the Cramer's rule suggests that to find the variables X, Y, Z, and many other variables, it is the determinant of the A matrix over the determinant over the general matrix. Okay, now the numerator here, the determinant of A matrix to the subset I, the I is representing several other variables you would have. So in this example, we have variables X and Y in our 2 systems. So it means that variable X is equal to the determinant of matrix A, but replacing the first column of the original matrix with the constant matrix. So as you can see, the constant matrix was 40, 28. Look at the general matrix, the coefficient matrix. It is 2, 8, 12, 4. So you could see that we've only replaced 2, 8 with 40, 28, which is the constant matrix. Now, let's look at the variable Y also. Variable Y would also mean A subscript Y, whereby the second column, which is the Y, is replaced with the constant matrix, 40, 28, keeping the first column, as it were, in the original matrix. So that is how we're going to do it. So if there were a third matrix, a third variable, then that would have been A subscript Z. That would mean you keep the first 2 columns, then the third column, you replace it with the constant matrix. Then you divide it by the determinant of the general matrix. So that's what the Cramer's rule is saying. Replace each column with respective constant matrix. So you're going to find a determinant for this. You find a determinant for this. When you divide, the result is the X value. You find a determinant for this. You find a determinant for this. When you divide, then you get the Y. So let's move ahead with examples. Now remember, the A matrix was formed with this 2, 8, 12, 4. And the B matrix, which is the constant, was 40, 28. Now, XAI, which is the X, AI, which is the X, we replace the first column of the general matrix with the constant. And that's how we had 40, 28 against 12, 4. Then for Y also, it's going to be 2, 8. We keep the first column and replace the second column of the coefficient matrix with the constant matrix, 40, 28. Then we find the determinants of X, we find the determinant of Y, divided by the general determinant of the coefficient matrix. So let's start with variable X. So to find X, that will be the determinant of this matrix So finding the determinant of a 2 by 2 matrix is the product of the diagonal elements. So 40 times 14 minus the product of the off diagonal. So this is the principal diagonal and this is the off diagonal. So you multiply 40 by 4 minus 28 times 12. That will give the determinant for this matrix. So you could see 40 times 4, that is 160. 12 times 28, 138, 136. You find the subtraction, then you get 176. Now, that of the principal matrix also, you find the determinant for this matrix. So product of this diagonal minus the product of the off diagonal. So that will mean 2 times 4 minus 12 times 8. You're going to get 8 minus 96, and that gives you this. So divide 176 by 78, then you get 2.27. So x is equal to 2.27. That of y also, you find the product of the diagonal, principal diagonal, 2 times 58 minus 8 times 40. 2 times 28 minus 8 times 40. And that of the coefficient matrix also is maintained. 2 times 4 minus 12 times 8. So we're going to get 56 minus 320 over 8 minus 96, and that gives us 3.38. So using the Cramer's rule, we resolve that x is equal to 22.7 and y is equal to 3.38. There's a simple approach using the Cramer's rule to solve two systems of equations. It could be used to solve the three systems of equations and more complex systems of equations, provided we are able to identify how to determine the determinants of each matrix. Thank you for taking time to go through this tutorial with us. If you're interested in several other videos, several other tutorials, you could subscribe to the button